Hello everyone, welcome to our talk Scavenger, Misuse Error Handling Leading to Qemu KVM Escape. This is a joint work with Anti-Security Latter Year Lab and Zhejiang University. First, who am I? I'm Xinwei Lin, a security engineer from Anti-Security Latter Year Lab, and my main research interest is virtualization security, fuzzing, and program analysis technology. And welcome security researchers submit vulnerabilities to Ant-Group Security Response Center. My partner Gao Lingpan will introduce himself in his presentation part. This is the agenda of our talk. Firstly, I will introduce the background of our talk, including Qemu, NVMe virtual device, and the error handling code usage in Qemu. Second, I will introduce that we got inspired from CVE 2020-25084, which is an use after free vulnerability because of the misuse error handling code. I will introduce that we applied directed gray box fuzzing to find vulnerabilities in error handling code. With the help of the fuzzing, we found an uninitialized free vulnerability. We named it Scavenger, and I will introduce the vulnerability details. Thirdly, my co-speaker Gao Lingpan will introduce the exploit development. Finally, he will do the conclusion and the discussion of the error handling code directed gray box fuzzing and the exploit primitive we used in this exploit. Okay, let's begin. This part, I will introduce the background, including Qemu and error handling code. Qemu is a generic and open source machine emulator and virtualizer. It supports multiple architectures such as IA32, x86-64, MIPS, Spark, ARM, RISC, and so on. Furthermore, it includes a huge collection of emulated devices, including NVMe controller. Qemu is widely used in security research. For example, IoT firmware emulation, AF-Qemu for black box fuzzing, dynamic instrumentation platform. However, Qemu has lots of attack surface, especially device emulation that attackers can write data to host machine from guest machine. High-quality vulnerability allows attacker to break out from a VM to control the host. Our vulnerability locates in NVMe virtual device. Here, we briefly introduce the NVMe device protocol. NVMe defines an optimized register interface, command and feature set to communicate between guest and host for PCIe SSDs. It minimizes MMIO writes in command submission and completion paths. NVMe has efficient support for I/O virtualization architectures like SR-IOV, which make it more and more popular in SSDs device emulation. Our work was inspired by CVE 2020-25084, which is a use after free vulnerability because of the misuse error handling code. This flaw occurs while setting up the USB packet. Because it doesn't check the return status of USB packet map function, which exists error handling code that free runtime memory. Then it uses the freed memory in the later code, which leads to an UEF vulnerability. This flaw results in a denial of service and potentially exploitable. So we can see in this code, it first invoke a USB packet mapped, and when it fails, Qemu will fix it by checking the return status, and if it fails, it will destroy the XGL structures and return the error code and to stop the following process. Let's see a detail. When USB packet map fails, it will free SGL structure. However, the vulnerable code doesn't check the return status of USB packet map. Then it will call USB handle packet, which will use SGL structure that leads to a UEF vulnerability. So from the code flow, we can know that it first free the SGL structure and then it uses the XGL structure. So it will cause a UEF vulnerability. And in the USB packet map function, we can see that if DMA memory map fails, it will go to error label. And in the error label body, it will call USB packet unmap function to free SGL structure and return negative number as the error status. This is a traditional error handling code pattern in Qemu. The caller is responsible for the correct usage of the function that contains error handling code. Inspired by CVE 2020-25084, we observed that the error handling code usage in the Qemu code, and we found that the error handling code can be classified into the following categories: resource release and the debug report. And the resource release category can be further classified into release memory or file handler or release logs. We can see that the debug report code just does the debug report and doesn't operate the runtime resource. So this category won't cause memory corruption, harmful behavior to Qemu. But in release memory or file handler category, the error handling code will release the runtime memory or the file handler in this code sample. We can see in this code sample, you will call Qemu IO free to free the buffer origin memory, and then you will F-close the file handler. So this behavior may lead to a UEF vulnerability if the caller code doesn't check the return value or status and misuse the freed memory. We introduced the CVE 2020-25084 is in this situation. And in the release logs, the error handling code will release logs in the code. This behavior may lead to a risk condition vulnerability. So from the code samples, we can see that misuse error handling code may lead to multiple memory corruption vulnerability case. Therefore, we think about how we can detect this type of vulnerability. So here we use directed gray box fuzzing in this fuzzing situation. That we want that the fuzzing process will go through the error handling code and all its caller site. We firstly do the static analysis. For the code samples in the error handling code, we can observe that the error handling code in Qemu is always jump from goto statement. Therefore, we firstly locate the goto statement in the code of the virtual device. We only fuzz one virtual device each time. Then we do the backward slicing analysis to get the caller side to the goto statement and the code body of the goto statement. We use the AFGO as our fuzzing engine, and then the information collected at step 2 is used as the feedback to the directed fuzzing engine. This is the whole fuzzing flow. In the pre-processing step, the code body of the goto statement is the target size of our fuzzing process, which will be used to calculate the seed distance. And in the fuzzing loop step, we are based on the distance guided strategy to perform the power schedule, and we take the caller side coverage into account to make the fuzzing process go through all the error handling code and its caller side code. So with the help of directed gray box fuzzing, we found an uninitialized free vulnerability, and we named it Scavenger. It locates in NVMe virtual device. This is caused because of the misuse error handling, and the NVMe is used to provide virtual solid state drive service, which, as we know, it is SSDS. And we use this vulnerability to win TIF Cup 2020 PAN contest, and it was fixed at version 5.2 0.0 of Qemu. Because we submitted the vulnerability to TFCAP official, so there is no CV assigned. The exploit environment is Ubuntu 20.04 host, and the guest is in the same environment. And it has full protection such as NX, ASLR, and PRE. This vulnerability locates in NVMe map PRP function. The function has two types of initialization. Type 1, it will initialize IOWAC, and type 2, it will init SG list. The three green box in this is the expected error handling SG list malloc free pair. So it firstly initializes the type 2 SG list, and if it steps into error condition, it will go to unmap label to free the QSG structure, which is initialized in above code. But what if the code flow doesn't obey the malloc free pair? Actually, we can control the code flow to firstly initialize IOWAC, and then we can control it to go to the error handling code to free QSG structure. And in this time, the QSG is in uninitialized status, which leads to an uninitialized free vulnerability. The misuse error handling code leads to an inconsistent malloc free pair. So this is the whole details of this vulnerability. And my presentation part is over. And my co-speaker Gaoning Pan will continue this talk. He will introduce the exploit development and do some conclusion and discussion. Thank you.
Hello everyone. My name is Gaoning Pan from Zhejiang University and Security Layer Lab. I'm also CTI player at AAA and AOE team. My background is trying to find vulnerabilities in hypervisors such as Qemu and VirtualBox. You can contact with me on Twitter there. And in this section, I'm going to talk about how to exploit this kind of misuse error handling bug and then escape the virtual machine. And we have quite a bit of challenges here, and we finally make it overcome this problem. And I think it is an interesting exploit. And now I will get to that. First, let's see what happens in these error handling functions. Qemu SG destroy. As talked before, by inconsistent malloc free pair, the argument QSG here represents a kind of uninitialized memory. And you can see that in this function, it's just to free something and just clear the memory. It's dangerous. You can see the red box here. It's just to free the first element SG in the uninitialized variable. And you know it's an uninitialized value, but if you can control the execution environment leading up to that, it is initialized because just put something there ahead of time. And that means if the attacker can control the uninitialized memory, you can free anything else. Although it is just a single uninitialized free vulnerability, it's totally enough for the attacker to launch the guest-to-host VM escape. And I'm going to discuss the exploit in the next. And here I want to show you the poke that how we trigger this bug. In this poke, the malicious guest will simply create an NVMe command for the device. And we will set a valid length in this command. And we could let the mapping fail and then turn to the error handling. So we can see that the Qemu will crash in this way. As a denial of service is nice, right? But we want to get code execution on the host. Well, it turns out that it's not easy. We need to confirm whether this structure is controllable by the attacker. So we want to know where does QSG comes from. By checking the source code and found the reference of the NVMe map PRP function, we found that there are 3 places to trigger this uninitialized free vulnerability in this vulnerable function. And each of them locates in different function as well as different memory regions, which means there are 3 options for us to construct an initialized variable. That's good. And let's take a look at each of them. In the first case, we can see that the QST data comes from a local stack area of memory. And it wasn't filled anywhere before it calls to vulnerable function NVMe map PIP, which leaves an initialized variable on the stack. And given an initialized stack variable, a straightforward idea is to see is there any controllable data at the same position on stack. However, we found that the NVMe device functionality is quite simple and the core stack is too shallow. When I turn to the base function that contains guest data and finds all the core places, we didn't find any controllable data in the stack. That means no attacker supply data could be written into the QST. This is a bit frustrating, but that's okay. When we look at the second case, this is almost the same pattern as the first case. Leaves an initialized variable on the stack and call the vulnerable function. But it's still difficult to control this initialized data for us. So let's take a look at the third case. You can see that the QST here comes from a global variable located in the heap. And this variable is allocated in the NVMe init SQ function. This function is just a new request structure and leave the QST member initialized. And after many function calls, it will finally go to the NVMe RW. And here we just pass its member QST as a parameter to the vulnerable function. And because this variable is on the heap, it thinks that we can control it. And because we can use some techniques like heap function, and that means we can control what we want to free. And now, given the heap initialized free vulnerability, here is a problem we run into that. Can we actually control what object to free? As I've said, like some techniques like heap function, we could make it to free anything else. And then we can turn to the initialized free to the arbitrary free. And another problem is that what object are we going to free? It's pretty straightforward to turn initialized to free to UEF because we know how to exploit UEF, but we don't know how to exploit an initialized free. So what should we do? We first found a structure that's under our control. Filling this structure before and filling the address fields with these address pointing to the object that we can control in the heap. Then we'll just malloc another request structure and trigger the initialized free. Then we will just free the object that we can control. At this moment, if we can read or write this object, then we got an UEF. Well, this plan is great, but actually, it turns out that is not easy. To make these things work, we first need a structure with a specific size. And this structure must have a pointer at a specific offset. And most importantly, this structure must be a powerful primitive. That the pointer here must point to a guest control object, which we can read or write. Notice that there should be a time window between the object allocation and the object usage so that we can use it after it was free. Well, after many tries, we didn't find such a structure because we not only need a structure to point into an object, but also this object should be completely controllable. That is too limited. For example, we found a structure in the NVMe and other traditional devices and some complexity devices. All of them cannot meet these requirements. Most of the structure in the Qemu are not yet controllable. It is almost impossible to find this kind of structure, and we can see that the Qemu's primitive is so limited. So it's difficult for us to decide what object to free. However, when I found that there is a different structure on both IO GPU device. Here we can see in this function, the device allocates an address mapping table. And this table is filled with the series of pointers and the length. And this looks like a grid structure. It has controllable size. It has pointer numbers. But differently, this pointer here points to the guest space. And this point just comes from a DMA memory map. And this is a key function which maps a guest physical memory into the host virtual address. And this address is what we have in this table. This means the Qemu can directly access guest memory in the host process. Well, can this structure help us to facilitate the exploitation? Maybe it does. Inspired by the mapping table on the VertIO GPU, maybe we don't have to find a reading, writer, and primitive in the host process. Maybe you can just use the buffer in the guest directly to help us to craft an exploit. Also, let's take a look at Qemu's process memory layout. In this picture, we can see there are two important memory regions. The first is the heap memory, which starts with 0x55. And the second is the guest memory, which starts with 0x78. And this guest memory is just backed by a single memory map region inside the Qemu KVM process. And notice that this guest memory is both mapped into the Qemu host process, but also exposed to the guest VM. We can think it as a shared memory between the host and the guest. From the perspective of the host, the guest memory can also be some kind of the heap memory, because they are both mapped into the Qemu process. So here's our idea. This is a high-level overview. First, the guests share the same memory with the host. In the host, any changes that we make it to the physical mapping regions are propagated to the memory on the guest. So now the guest is aware of the host operation on guest memory. And more importantly, the guest can read or write its memory at any time, right? So it will naturally provide us a reading and writing exploit primitive. We don't have to find a reading and write primitive in the host. And finally, it's quite easy to make a fake chunk in the guest. We just need to fill in the chunk with the chunk header, just like chunk size and some flags. So what if we directly free a fake chunk in the guest system? Here I want to show you what if we free a fake chunk in the guest. The left is the debugger. It shows the T-catch pins in the host overview. And the right is what we have done in guest. You can see that we make a fake chunk and trigger the initialized free variability, and then the fake chunk is inserted into the host T-catch bins. Wow, that's amazing. Because of the ptmalloc in Linux, this chunk will point to the first chunk in the T-catch free list. And this will leave the first chunk address in this new chunk. And as expected, by reading the buffer after the initialized free, we leak the heap address of the host. Yeah. This means our method truly works, and the guest and the host share the same memory. They can operate on the same chunk. We can use this attack to facilitate exploitation with the help of the guest memory. So let's take a summary. Traditionally, when we craft an exploit to escape the virtual machine, we'd like to find some data structure in the host process to help us to manipulate the memory layout. We name it as host-to-host attack. And here, we are processing a cross-domain attack, which manipulates the memory across the hypervisor domain. This is the most interesting part of this research. And it's basically like this. We first make a fake chunk with a valid chunk header in the guest system. And in the host space, we just fill in the memory before with the address pointing to the guest's fake chunk. And then we just malloc another initialized request structure, trigger the initialized free, and then we will get guest chunk in the host heap. And because the attacker has a full privilege in guest system, he can read or write his memory at any time. So now the problem is turned to an UEF. With this powerful primitive, we can make it to exploit this uninitialized free, just like to exploit an UEF vulnerability. Okay, now the problem is turned to exploit an UEF vulnerability. The problem becomes more easy for us. And then I will discuss the details step by step. First, we need to find the information leak to bypass ASLR. And then we need to manipulate heap layout to hijack the control flow. And finally, we execute arbitrary commands and get the code execution on the host. Before we start, we have to do some heap splitting. In order to get a stable system heap layout, we just use the NVMe init-sq function here on the right side. And this function can be called a lot of times to split a lot of chunks. We just call this function a whole bunch of times to clear the Tcache bins. And this way, we can prevent the following free chunk to be consolidated into a larger chunk. And thus, we can get more reliable exploits. So, looking at more graphically, in order to bypass ASLR, we need to find the information leak. First, we make a fake chunk in the guest, and this gap was filled with reading data we put in. And this chunk is with the size of 0x290. Then the guest writes value to the MMIO interface to lead up the device main execution. And in the host space, the vert IOGQ device in the hypervisor will malloc a mapping table filled with the edges pointing to the guest fake chunk. And this chunk is filled with the size with 0x150. And then we'll just free this mapping table. And this freed chunk will be inserted into the Tcache bins. And that will actually leave us with the chunk in the state that we have left it before. In the next, we'll just malloc an IO request structure. And this structure will just fill in the position that we have initialized before. With this, with the initialized field pointing to the guest chunk. We have to call those two malloc in order because if you do anything else between these two operations, you've just used the heap for something else. So we have to be very careful about that. Then we'll just go after buggy code and trigger the free vulnerability. Since we have made a fake chunk in the guest, the host will treat it as a normal heap chunk and push this free chunk to its Tcache bins. And this will leave a heap edges in the header of the fake chunk. Then, since we know what's in memory now, and we can actually reliably leak the host heap edges by just reading the buffer in the guests. Of course, only heap edges is not enough. We have to find some other edges as well, such as physical mapping edges, Qemu binary edges. Then we just map another mapping table with the size of 0x219 to fill in the chunk located in the guest space. And the pointer here in this table just points to the command chunk located in the guest. We just initialize this command buffer for the code execution stage. Well, the same as before, we could also leak the physical mapping edges by just reading the buffer. These edges represent the host virtual edges, which maps into the guest physical memory. And with these edges, we can just know where the guest buffer is to the guest, to the host. In order to hijack control flow, many previous work just use the timer structure, which has a function pointer, and this is a good structure. And if we get such a timer, we can easily leak the Qemu binary edges and hijack the control flow. So let's do it again. Make a fake chunk in the guest with the size of the timer size. Construct another uninitialized IO request structure with a pointer pointing to the fake trunk in the guess. Then we have to get a malloc primitive to malloc timer. Fortunately, in NVMe device, there is a primitive to malloc new timer. We don't have to find it any other places. Then the idea is just that, and we just trigger the initialize free and malloc Qemu timer to fill in the trunk in the guess. Finally, we will get the timer into the guess. And now, since the timer is located in the guess, we can easily read and write this structure. In this way, we can link the Qemu binary edges. With these edges, we can directly calculate the offset of the target function in the binary, and we can easily get to know where is the system function. System function is the key function if we want to get a code execution. And after that, we'll override the system function, the function pointer in this timer to those edges to the system function, and override the first argument in this timer and to the command buffer, which we have set up before. And this edges is some kind of physical mapping edges. And in this way, we will get an IP control. And finally, by just expand the timer to trigger the timer's callback, we actually execute the system GNOME calculation. And this way, we manage to hijack control flow and get a code execution on the host. And this is a demo of the VM escape. By running our exploit code in the guest system, we finally make it pop a calculator in the host. In fact, you can run any code that you wanted. So the exploit is over. But here I want you to know this exploit is different in several ways. For example, in the attack surface, previous VM escape locates in the USB module, SLIP TCP IP emulator, and AMD API driver. But we target the NVMe storage device. For vulnerability types, almost all previous vulnerabilities are caused by buffer overflow. However, our case is an uninitialized free vulnerability in error handling code, which requires more iterations and triggers in the vulnerability exploitation. And for exploitation technique, previous vulnerabilities are almost the same, finding controllable data on the host process and construct exploit primitives such as arbitrary write. Instead, we utilize the data placed in guest memory, which naturally provides us a reading and writing primitive, which is manipulating memory across the hypervisor domain. Further, I want to show the additional analysis of this attack. As long as the attacker has such a vulnerability which can arbitrarily control what object to free, the Qemu can be exploited. Because the techniques of cross-domain attack is general, we observe that there's no memory isolation, the memory randomization mechanism in Qemu, such that we can utilize the user space memory to facilitate the exploitation. And we attribute this feature to that the chunk is not encrypted in the Linux, so that we can easily make a fake chunk. But it may be difficult to launch the attack if the chunk header is encrypted, like in Windows. And finally, we believe this kind of attack may also affect other hypervisors like VirtualBox, VMware, and so on. So what can we learn from this research? First of all, I hope you now understand more about misuse error handling. Error handling code is used extensively in hypervisor, which is this is the area where you want to hunt for issues and vulnerabilities. And second, I hope you know our error handling directive fuzzing will make you text hard to find bugs existing in error handling code effectively. And finally, we've shown that guest memory can also bring us more attack primitives. I hope you now understand how to facilitate exploitation with the help of the guest space memory. And I published the exploit on GitHub. Okay, that's all I have today. I hope you enjoyed it. Thanks for your attention.